Alright, so this video is one in which we'll go through a handful of problems on energy conservation and work, just to get the hang of solving problems like this. We start off with three formulas or definitions. K, meaning kinetic energy, is calculated as 1/2 times an object's mass times its speed squared. U, which in this case represents gravitational potential energy, U being potential energy, in this case it's understood that it's gravitational, is an object's mass times its acceleration due to gravity, which on Earth is 9.8 meters per second squared, times its height above some reference point, and work being a means of transferring energy equal to FD cosine theta, where F is a force, D is a displacement, and the angle theta is the angle between the force and displacement vectors. For the first problem, we start off with an equation that captures the idea of energy conservation. An object's initial kinetic energy plus its initial gravitational potential plus any work done by friction, this is typically negative, and subtracts from the total mechanical energy, plus any work or energy transferred in from the outside. This can be a positive increase in energy or a negative decrease in energy, results in a final kinetic energy and a final potential energy. If there's no friction and there's no outside forces doing work, these two are zero, and the mechanical energy that we start with is equal to the mechanical energy that we end with. If this one's zero and this one's negative, then our final mechanical energy ends up being smaller than our initial kinetic energy by this amount. We're always keeping track of energy. So here we have a 45 kilogram diver standing motionless at 12 meters above a pool. The diver steps off the board and falls. How fast is she going 3 meters above the water? I'm going to basically rewrite this equation right below here. In place of K, I'm going to write 1/2 mv squared. In place of U, I'm going to write mgh, plugging in my initial height. If there's any friction, I'm going to calculate it, and the work that it does using FD cosine theta, etc. So we start off and we say, look, the person is motionless, so there's no initial kinetic energy, so that's zero. The person does have initial gravitational potential energy of mgh, and so we say that's, well, we're just going to write it as a formula now. We're not going to plug in the numbers yet. And I put h sub I to show that's initial height. This is assumed to be a frictionless fall. The air resistance is insignificant, and so we say there is no work done by a non-conservative force, namely friction, and there is no work done by an outside force, such as a rope attached to the person, pulling the person, tension or some sort. Nothing there. 3 meters above the water, the girl has both kinetic and potential energies. Her kinetic would be 1/2 mv final squared, and her potential would be mgh final. And now we solve this for our final speed. How fast is she going? 3 meters above the water. Notice that the m's can cancel out because there's an m in every term. We don't actually have to know that she's 45 kilograms. So what I'm going to do is I'm going to subtract mghf over to the other side, and I'm going to get mghi minus hf. I've subtracted that term over, and then I factored out the m and the g. This is going to equal 1/2 mv squared. The m's can cancel. Algebraically, I'm trying to find vf. I multiply both sides by 2. And I take the square root. That gives me my final speed. This is going to be equal to 2 times 9.8 meters per second squared times 12 meters minus 3 meters. And we take the square root of that, and we get 13.28 meters per second. For problem 2, a 1.65 kilogram bird is flying 2.5 meters per second at a height of 10 meters above the ground. The bird is shot, oh dear, falls as a projectile towards the earth. What is the bird's speed upon reaching the ground? But don't say 0. We start with the same equation, and we say that the bird starts off with kinetic energy of 1/2 mvi squared, starts off with potential energy of mghi. As a projectile, there is no significant air resistance. There is no work done by friction, a non-conservative force. There is no work done by an external force. We have speed. At the end, but at the end we are at ground level. Height is assumed to be 0, and so we have no potential energy mgh equals 0 because h is 0. In this case, we can divide through by m. We want to find our final speed, so we can multiply every term by 2 to get one step closer to isolating the VF. That gets us VI squared plus 2GH sub I equals VF squared. Some of you might recognize that as a kinematic equation as well. That tells us that the final speed is equal to the square root of our initial speed squared, which is 2.5 meters per second squared, plus 2 times g, which is 9.8 meters per second squared, times our initial height, which is 10 meters. When we take the square root of all of that, we get 14.22 meters per second. Number 3, how much work does it take to increase the speed of a 1,000 kilogram car from 5 meters per second to 20 meters per second? Here there's a direct reference to work. This problem feels a little bit different than the two before, and indeed we solve it a slightly different way. I take the equation from before and I rearrange this UF, I subtract over here, this KI, I subtract over here, and I get this equation in a slightly different form. I realize that the change in my height, initial minus final, is equal to the work done by the conservative force of gravity. Furthermore, this plus this plus this will equal the total amount of work done on the system, on the car, and this is equal to the change in kinetic energy. This is the work kinetic energy theorem. The total or net work done on an object is equal to its change in kinetic energy. We want to find out the overall work done, how much work is done, and so we need only find the change in kinetic energy to have our answer. So we say the net work done is equal to my final kinetic energy, 1/2 mv final squared, minus my initial kinetic energy of 1/2 mv initial squared, and that is equal to 1/2 times the mass of 1,000 kilograms times a final speed of 20 meters per second squared minus 1/2 times 1,000 kilograms times my initial speed of 5 meters per second squared. This equals 187,500 joules. So my answer, how much work does it take to increase the speed, is 187,500 joules. Number 4. A 2.6 kilogram baseball is thrown straight upward at a height of 4 meters above the ground. It's moving upward at 30 meters per second. How high is it when it has slowed to 4 meters per second upward? We start with our same equation. We start off with kinetic energy. It is moving 30 meters per second initially. We have 1/2 mvi squared. We start off with potential, gravitational potential of mghi. There is no work by a non-conservative force. There is no work done by an external force. And we end up with both 1/2 mv final squared and mgh final. We want to find our final height. At this point, we're just simplifying. We'll start off by dividing every term by 1/2 m. That leaves me with a vi squared. That leaves me with a 2ghi. On the other side, that leaves me with a vf squared. And that leaves me with a 2ghf. I can now subtract the vf squared over to the other side and get vi squared minus vf squared plus 2ghi equals 2ghf. I can divide both sides by 2g. And then I obtain this expression. Substituting into this expression, we have, let's see if I can fit this in, initial speed squared, which is 30, minus final speed squared, which is 4, plus 2 times 9.8 meters per second squared, times my initial height, which is 4. All of this divided by 2 times 9.8 meters per second squared. This equals 49.10 meters. That is my final height. Moving right along, we come to number 5 of our sample problems. A hockey puck of mass 0.10 kilograms is moving at 12 meters per second. A hockey stick applies a force of 20 newtons over a distance of 0.3 meters in the direction that the puck is already traveling. This causes the puck to speed up. What is its speed following the impact? This problem is one in which, again, we need to rearrange the original equation. We're dealing with work here, and so we rearrange it so that we have the total work is equal to the change in kinetic energy. Again, that's the work kinetic energy theorem. There is no work done by a conservative force. There is no work done by gravity. There is no work done by friction that we are aware of. This is an ice skating rink. Typically we assume that friction is negligible on ice. The work done by the external force, by the hockey stick, is Fd cosine theta. And the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. So we want to find this final speed. To do that, I'm going to add this term to the other side and get Fd cosine theta plus 1/2 mvi squared equals 1/2 mv final squared. And now divide all terms by 1/2 m. That gives me 2FD cosine theta over m plus VI squared equals VF squared. I can substitute into this expression right here, take the square root in order to get VF by itself. We're going to have 2 times our force. Our force is 20 newtons. Our distance, the magnitude of displacement, is 0.30 meters. Because the force and the displacement are in the same direction, the angle between those two vectors is 0 degrees. Cosine of 0 degrees is equal to 1. So we really could leave that out. We divide this by the mass, which is 0.10 kilograms. We tack on a initial speed squared. That's 12 meters per second squared. We take the square root of this large expression, and we obtain our final answer of 16.25 meters per second. For number 6, a 70-kilogram man jumps from a burning building, aiming for a net held by a team of firefighters. He flings himself forward at 2 meters per second from a window that's 20 meters above the ground and 18.5 meters above a net. How fast is he traveling when he reaches the net? He starts off with kinetic. He starts off with potential. We're going to say there's no work by a non-conservative force or an external force. And he ends up with, well, he does end up with kinetic. And whether or not he ends up with gravitational potential energy depends on where we set our zero height. If we set our zero height at the net, then this becomes 18.5. If we set our zero height at the ground, then this becomes 20. So let's set our zero height at the net. Now HI is 18.5, HF is 0, this becomes 0. Do it the other way and you'll see you get the same final answer. We've already solved a problem like this. We get VF is equal to the square root of VI squared plus 2G HI. That is, VF is equal to the square root of 2.0 meters per second squared plus 2 times 9.8 meters per second squared times the height of 18.5 meters. And that comes out to 19.15 meters per second. Finally, number 7. Number 7 is much easier and more straightforward. It's just calculating work using the equation. Work is FD cosine theta. A weightlifter lifts a 45 kilogram dumbbell 0.8 meters from its starting position, lifting it at a constant speed. How much work has he done on the dumbbell? The work is the force needed to lift something at a constant speed. This object has a weight, and it has an applied force upward. On these balance. Only by balancing is the object not accelerating but moving at a constant speed. The object's weight is its mass times 9.8, which turns out to be 441 newtons. Thus, to raise it at a constant speed, you must apply a force of 441 newtons. If you apply a larger force, it will accelerate upward. The work done by the man lifting the weight is the force that he applies, 441 newtons, times the object's displacement upward, 0.8 meters, times cosine of 0 degrees. As the force and the displacement are in the same direction, the angle between those two vectors is 0. This comes out to work of 352.8 joules. That's how much work he does lifting the dumbbell. You'll be able to easily prove that the work done by gravity is negative that amount, and the total work done is 0. But that's not what it's asking. Okay, that's it for now.